This is a video for how to go about creating a linear graph with an R-squared and an equation value for activity 4.1.5 Cams in Motion for your Introduction to Engineering Design class. Please note that in the info section directly below this video there is a link to the spreadsheet that you see in the video right now, and you can click on that link and follow along if you choose to. The data that we currently have on our spreadsheet is just a nominal diameter of a cam and the maximum displacement of a pair cam. Now the nominal diameter is a given value that we have referenced in other videos for creating cams for an automata box. So if we were to create a cam and put it inside of an automata box, we would want to know that when this cam rotated to where its maximum height would be, which we'd be rotating this cam 180 degrees to where this was up here at the top at 12 o'clock. We want to know what the highest distance is that this follower would be pushed up based upon the diameter of the cam. So if by chance you are curious as to how to reference this in Fusion 360, I have an automata box and I've put 4 different cams in there, and we're only going to pay attention to the pair cam in this case. So I'm going to come over and turn off the visibility of the eccentric cam, the heart cam, and the hexagon cam, and I want to edit the diameter of just the pair cam. So I'm going to go to edit real quick, and I'm going to say capture position, and I'm going to go to modify. I'll go down to change parameters, and when this box comes up, you're going to notice that we're at 1.5 right now, and I even have this all the way up, and I know that we're only looking at the cam in full color right now, but I can tell that this is actually down below my ruler a little bit. So I'm going to change that to, let's say, 2 inches, and I'm going to hit enter, and it's going to jump up to 2, and I'm going to say okay, and I'm going to go to finish, edit, and place. And because we have those tangent relationships, I can see now that this cam is rotated at the correct degree, and we're only touching just the bottom of this. There's a tangent relationship between the bottom of the follower and the cam itself. And if I look up here at the top, it looks like I have about an 1/8 of an inch relationship right here. Now, just for reference, the equation chart that we're going to be making in the linear graph is all going to be based off any data you get off a physical automata box or a Fusion 360 automata box as well. These are just data that you can place in and get the readings from and understand what the equation and R value is for the chart. So it's not necessarily 100% a big deal if you have the exact same data that you see on my screen. We're just going to be referencing a nominal diameter of 1, 1.5, 2, and 2.5 and create a chart off of this data. We're going to pretend that we've taken readings on that ruler, and the readings that you see below the diameters are correct. You can go back in and change these as you go through with a physical automata box or a virtual automata box in Fusion 360. To make the linear graph, we are going to highlight all of the information we see right here that's highlighted in blue. We'll go to Insert, and we're going to go to Chart. And when we go to Chart, you're going to see automatically we get for ourselves a linear graph that tells us that, if we're at this 0 point right here, how high up is the first, how high up is that highest point on the follower going to be if we have a nominal diameter of 1? And you can see that's 0.125. This line follows this chart. Now, in order to get the R-squared value and to get the equation, we're going to go to Customize. When we go to Customize, we want to go to Legend. And when we go to Legend, you can see in here, excuse me, we need to go to Series, I apologize. When we go to Series, let's go to Series, and we're going to go down to something that says Trend Line. When we click on Trend Line, we want to say it wants to show the R-squared value, and automatically we're going to get an R-squared value here of 1. We want to also see the equation. So when we go to Label, we're going to go to Use Equation, and the equation is 0.125x plus 0. And what that means is that if we're at 0 here, the 0 value, if you will, of the chart is always going to be 0.125. That's where that cross is right here. That's where the X and the Y would cross in this case. I know we have a 1 down here, but the reference value in this case, because it's the beginning of the chart, would be 0. The R-squared value is a 1. That means that it makes perfect sense that every time we increase over an amount, it goes up an amount. That's what the 1 for an R value is. If this was an 83%, we would be all over the place, let's say a little bit, to say that we don't have a perfect linear relationship between our X and Y value. You'd say 83% of them have a good relationship between the X and Y values, 17% do not have that relationship. One thing we can notice is the difference in numbers between each one of these dimensions. So up here at the top, these distances, if I hit equals and I say my 0.1875 minus my 0.125 and hit enter, I'm going to get 0.0625. I should see the same if I say that I want 0.25 minus 0.1875. These are the exact same numbers. Now you're getting a little bit of a line across the bottom here. Doesn't really matter that much, but the point is when we have this r equals 1, that means that as we go up in the y direction, we'll have the exact same value in the x direction, and so on and so forth. That's what that r squared 1 value means. So to create this chart allows us to see that relationship when we change the nominal diameter of a cam and how that top of the follower relates. So when we use cams in Fusion or physically, we should be able to predict when we change the nominal diameter of the cam exactly how high up the follower will go. When you make these boxes in Fusion, and you make them physically, the cams and followers might be different heights. You might have to go in and measure things and try to get a good prediction from your charts, because the point is to understand the mathematical modeling and prediction behind what you design for anything that might have motion or movement to it. So you can go to a chart or a graph and be able to predict the behavior of your automata box and make all of your designs to fit that behavior and criteria. So this has been a video for how to go about creating a linear chart with an r squared value and an equation for activity 4.1.5, cams in motion, for your Introduction to Engineering Design class.